In this video, we will talk about reliability. Reliability is a property of a measurement that has to do with the degree to which the measurement is free from error. The idea is that when you measure something, for example, when you administer a test to someone and you obtain a test score, that is your measure, your variable. This is supposed to include two things. One thing is the true score. So how much you should get to indicate this person's true ability on this test. All of the skills that are required to perform on this test, accurately and objectively indexed, would result in a true score. But you don't ever get exactly the true score because there are various sources of error. There are many different sources of error. Some can be biased, some can be unbiased, but you never get exactly the true score. For example, a person may be distracted in one moment, better concentrated in another moment, or a person may be in good form one day or a bit sick on another day. And each time, at each question or each test item, there is a probability of responding according to one's true ability, but there is also a probability of error. And a reliable test is a test in which you don't have measurement error, or that you have as little measurement error as possible. When you have a lot of measurement error, this implies that if you administer the same test again, you will get a different score. And if there is a very large amount of error, then the two scores will be very different. In fact, there are different kinds of reliability, and they have to do with the extent to which measures are repeatable, robust, and internally consistent. What does this mean? A measure is repeatable when you get the same result at retest. So you administered the same test twice and you get the same score. Usually you don't get exactly the same score, and the extent to which the scores are likely to differ is your retest reliability. There are many kinds of tests for which there are different variants or alternative forms that are supposed to measure exactly the same skill. A test is robust when these alternate forms produce the same outcome, that is, the same value on your variable, the same measurement. Usually you don't get exactly the same measurement, and it is the alternate form reliability index that measures the extent to which your two scores are similar to one another. And finally, we have what we call internal consistency. Internal consistency concerns measures that are composed of different items, as is usually the case with assessment tests. Internal consistency is what we're mostly concerned with in this short video, in which I will show you how the most commonly used index of internal consistency is computed. Internal consistency reflects the extent to which the different items of a test produced correlated outcomes. That has to do with the idea that if all the items in a test measure the same thing, measure what the test is supposed to measure, then if you're likely to do well on one item, you're also likely to do well on another item. Imagine a spelling test that has 10 words, so you dictate 10 words. You want a good speller to actually be able to spell these words correctly, and you also want a poor speller to make mistakes on spelling these words so that your test can distinguish them. For a test to be internally consistent, it means that a person who is likely to get one word correctly is also relatively likely to get other words correctly spelled. Whereas a person who is likely to misspell a word is also more likely to misspell other words as well. That expresses the idea that all the words that are included in the test should be assessing the same thing. So a person who is not a good speller should be less likely to misspell all of the items compared to a person who is a good speller who should be more likely to spell all the items correctly. Of course, there are differences in difficulty between the items. So you're not expected to be equally likely to spell them all correctly or all incorrectly. That is not the point. The point is that in relative terms, a person who spells one word correctly, so is more likely than another person to spell one word correctly, should also be more likely than another person to spell the other words correctly. So it's all relative, even if individual words are spelled correctly at different rates. That's what internal consistency reflects. All these different forms of reliability are assessed with some way of correlation analysis. Retest reliability and alternate form reliability are usually just a simple correlation test. But internal consistency is a little bit more involved because there are multiple items. So here we are concerned with a specific index of internal consistency, which indicates the degree to which different parts, different items of a scale are aligned with one another. They are interrelated. They are all pointing in the same direction. So a positive value in one item is associated with a positive value in other items. For the example we use for the calculation, we have a motivation scale with 10 items. So 10 different questions that have to do with motivation. So K is the number of items, which is equal to 10. Each person responds to each question by a rating between 1 and 4. For example, one question might be, how important is it for you that you do well in your exams? That is a motivation question, and you could have 1 meaning I don't care at all, to 4 I'm extremely concerned I have to do well, and 2 and 3 would be intermediate. So each one of the K items is responded to by each person with a rating from 1 to 4. And for this example, we have data from 51 participants. So sample size N is equal to 51. And this is what these kinds of data look like. We have the 51 persons here, 1 per row. We cannot show all of them on one slide, so these are omitted. And we have our 10 items, our 10 questions on 10 columns. Each person responds to each item by a rating, a number from 1 to 4. 1 indicating lack of motivation and 4 indicating maximum motivation. And for each person, the sum of all of these ratings is their score on the scale. So 35 is the sum of all the ratings for the first person. 36 is the sum of all ratings for the second person, and so on. And on the bottom here, I'm showing the standard deviation of each column. So the first question, the first item with these values has a standard deviation of 0.58. The second item has a standard deviation of 0.24, so less variation here. The third item has a standard deviation of 0.96, so more variation in the third question. And there is also the standard deviation of the total scores. Each person gets a total score, and this is the standard deviation of the total scores. And the square of this is the total variance in this test, is the variability in test scores that we're interested in examining. A reliable test is a test in which the total variability is accounted for by true differences between the persons. And that happens when the different items are all closely related to one another. So if there is no error, or if there is little error in individual responses to individual items, then these items will be very highly correlated with one another and will thereby take up most of the total variance of the test scores. Let's see how that works out. The first thing we need to do is to calculate a correlation matrix for the item scores. So the correlation between question 1 and question 2 is the correlation between these scores, these values, and these values. Remember that persons 5 through 45 aren't shown, they're in here. The correlation between question 3 and question 4 is the correlation between these values and these values, and so on. For each pair of items in the test, we compute a correlation, and that is the output. So question 1 through 10 here, and question 1 through 10 here. The correlation between item 1 and item 2 is 0.15. And of course, it's the same as between item 1 and 2 in the other direction. So these are symmetric. The correlation between item 2 and item 4 is 0.16. And of course, it's in both directions. And I have also indicated on this the standard deviations of the items, which we're going to need. First of all, note how many these are. So there are 10 items and 10 items in rows and columns. So there are actually 100 cells here. 10 by 10 is 100. So in the diagonal, which I have deleted, are the correlations of each item with itself. So Q1 with Q1, which is always equal to 1. So there is a bunch of ones here, which I have removed so you can more easily see the rest. So 10 by 10 is K squared, is how many cells we have here in this matrix, but we have removed 10 because they are the correlations with themselves and they're equal to 1, and they don't vary at all. In other words, they're always 1. So there is 90 cells left, which depend actually on the scores of the items. 90 is 9 times 10. So instead of K squared, which is all of them, 90 is K times K minus 1. So 10 times 9 is how many cells we have in this correlation matrix that aren't fixed to 1. This is the number of intercorrelations that are not 1, whereas all of the cells are K squared. What we need to do now is we need to measure how much of the total scale variance is accounted for by each pair of items. To do that, we need to compute the covariance between items, how much they covary. Ideally, for a consistent test, all of the variance in the test scores is due to covariance between items. So ideally, we want the items to covary a lot, indeed as much as needed to account for all the test variance. If there is extra test variance that is not accounted for by item covariance, that indicates error in measurement, so lower reliability. To compute a covariance, we need 3 things. So the covariance for items 1 and 2 is given by the product of their correlation with their standard deviations. So the covariance of Q1 and Q2 is equal to the product of their correlation with their standard deviations. That's because the standard deviations are measures of how much these vary. Remember, the standard deviation is an index of dispersion. So the standard deviation of question 1 is an index of how much question 1 varies. The standard deviation of question 2 is an index of how much question 2 varies. And the correlation between question 1 and question 2 is an index of how associated they are. So the product of these things is called the covariance and is an actual measure of how much they covary. If we do this for every pair of items and we add all of these up, then we will end up with a total covariance that is related to the items. And that will lead us to the calculation of alpha according to Cronbach. In fact, this is not how you will see the formula in most textbooks, but I have rearranged it in an equivalent way that makes it easier to see what it is composed of. So this is a variation on Cronbach's alpha, although of course the result is the same, that makes it clear how alpha is calculated based on the test quantities. So first, let's start here. This is a covariance. So correlation multiplied by standard deviation and standard deviation, correlation between the I and J items multiplied by the standard deviations of I and J, and that is summed for all the rows and all the columns, excluding the diagonal, so not when I equals J. So what this means is basically add up all those numbers that I showed you before in the table. Just add up those 90 things that are made up of these products, correlation times standard deviations. So this is the sum of all covariances. And then that's divided by how many they are. K times K minus 1. This is 90 in the example. So this is the average between item covariance. Each pair of items contributes to this, and we calculate the average. This is the average covariance. And if we move on to the denominator, which is another fraction, this is the variance of the total scores in the test. So this is the total variance in the test that we want to account for. This is how much test scores vary. If the test is consistent, all of this variance is useful. It's not error, but is contributed to by covariance of items. So this is what we want to account for, and we actually want to divide this by k squared because we want the average variance per cell. Remember, we had 100 cells in that matrix. So the variance of the total test scores that is assigned to each cell on average is this ratio. If there are 100 cells, each of the cells should account for 1/100th of the total variance. And this is how much it actually does account for. So alpha, in a sense, is the proportion of total scale variance per cell, so per item pair, that is actually accounted for by item pair covariance. If all of this is accounted for by this, if these are equal, then alpha is 1. This is actually never the case in real data. But if the items are not correlated, if the R's are 0, so this is going to be 0, and alpha is going to be 0. If the items are unrelated, alpha will be 0. if the items are very highly related so that their covariance, their average covariance, approaches the portion of the total variance of the test that corresponds to each cell, then this average is going to approach this portion of variance, and so alpha will approach 1. So alpha is near 0 for inconsistent scales that have uncorrelated items. We never use scales with low inconsistency, of course. And alpha approaches 1 for consistent scales that have highly correlated items. This is what we want, what we strive for in making a test. Indeed, there are some guidelines, for example, that reliabilities are very high if they exceed 0.9. And some people say that there are different levels of acceptability, that we should not be using tests with internal consistency below 0.7. There is some variability here in how high we want this consistency to be in order to consider that our test is reliable. But regardless of any such fixed criteria, alpha does quantify the extent to which item covariance accounts for the variability in test scores. It turns out that this alpha is actually equal to the average correlation of all split half pairs after it is adjusted for standard deviations and smaller size. What is a split half pair? A split half pair is a split of your test into 2 halves. So this motivation scale has 10 items. We can split it in half by having 5 items in one half and 5 in the other. And then treat these as 2 scales and compute their correlation. So the correlation between the first 5 items and the second 5 items, that is one split half pair. However, there's lots and lots of possible split half pairs. We could have items 2 through 6, and then that's one half, and then items 7 through 10 plus the first, that's another half. Or we could have the odd numbered items being one half, even numbered items being another half. There are many ways we can split 10 items in half. If we do all the possible splits and calculate the correlations for all of them and adjust for standard deviations and reduced sample size, then the average of all those is equal to alpha. So this is a different and equivalent way to think of internal consistency in terms of alpha. In general, to sum up, scale reliability as a concept includes different ideas. There are different kinds of reliability, such as test-retest, alternate form reliability, and internal consistency. And they all have to do with correlation. So test-retest is the correlation between 2 administrations of the exact same test. Alternate forms is the correlation between the scores on 2 versions of the same test. And internal consistency is an index that quantifies the variability in test scores that is accounted for by covariance among the items. And there are different ways to calculate that. There are many different ways. There are different indices. Cronbach's alpha is the one that is most commonly used, the one that you're most likely to see in the literature. It has been heavily criticized since its inception because it depends on assumptions that are actually very rarely satisfied. Although the assumptions are not satisfied or are difficult to check, people still use alpha a lot. However, in recent times, we see increasing use of other kinds of indices that are much more complicated to calculate, but are not based on the same assumptions. And now that we have these programs to calculate everything for us, the complicated calculations are no issue. So in your studies, it is recommended that you also report internal consistency in terms of omega, one of the several variants of the omega indices of internal consistency, in addition to the commonly used Cronbach's alpha.